All right. Good morning, everyone. So let's get started. Again, just remind you that homework number 4 is due on Tuesday next week. So it's only a few days from now. Make sure you allocate some time during the weekend to get started. Okay. As usual, some of the problem might be challenging to you. You might also have to review like some of the knowledge we learned from the previous semester, primarily on the vectors. Okay. All right, so let's take a look on what we learned last time. So last time we talked about electric potential energy. So basically this is an analog to gravitational potential energy. So in a similar fashion, um, so change in electric potential energy is QED. E is the electric field, D is the distance, okay, that charge move. Similar to MGD, okay, so that's the about similar expression there, where E is the electric field, G is the gravitational field, okay. We also talk about the potential field, which is equal to the change in electric potential energy divided by the charge Q, all right. So in that sense, electric potential energy is equal to the charge times the electric potential, okay, or in this expression here. Um, so for electric field, it's similar to gravitational potential field. So then electric force is similar to gravitational force, which is also a conservative force. Okay, so in that sense, then energy is conserved if you have kinetic energy plus the potential energy that at point A should be equal to the sum of the two at point B. Okay. In this case, electric potential energy is equal to Q times V, where V is the electric potential. So there are two V's here. Small v is the speed, capital V is the potential, electric potential. Okay, so then you can rewrite the term. So this equation can be written as kinetic energy at point B equal to kinetic energy at point A plus Q times the difference in potential energy at point A and B. Okay. All right. And we also took a look on the electric potential in a uniform electric field. Okay, so potential then is equal to, if this is a uniform field, then it's equal to electric field times the distance from point A to B. The difference of potential in point from point A to B is equal to that V. So this is referring to change in potential energy. Okay, you can use the subscript. That means potential difference from point A to B equal to E times D, or in another way, if you are looking for E field, then it's equal to potential difference from point A to B divided by the distance between A and B. All right. So today we'll be looking at the electric potential due to a point charge. Okay. Now, if you have a point charge here, remember then the electric field is pointing away from the point charge. If this is a positive charge. Okay. So you can see electric field. And then we learned that electric field is KQ over R squared. So you can see in this case, if you have an electric field produced by a point charge, then the electric field actually is not uniform. It decreases as distance increases away from the source of the point charge. Okay, so as you are away from the point charge, your electric field actually decreases. So what's then the electric potential due to a point charge? Okay, so this can be mathematically calculated. So if you guys see this sign that you are not familiar with, that means you haven't taken calculus, but it's okay. We are not going to require you to do any integration here. So this sign says integration. Okay, I just want to put this up so you know that the potential, electric potential for a point charge actually can be calculated by doing integration. All right. So, but you just need to know the result. Okay. So then the result is the electric potential energy from point A to B, the difference, okay, is equal to, or UA, electric potential energy at point A minus electric potential energy at point B, is equal to Q0 over RA minus Q0 over RB. Okay, so potential energy for a point for in the field that is produced by a point charge then is equal to this U equal to Q times V, where V is equal to KQ over R. Okay, so this is just that the result that you need to know. You don't have to do the integration, or you don't need to know how to do the integration. All right. So for electric potential by a point charge is KQ over R. At this point, maybe it's appropriate to do a little bit of summary on for point charge. Okay, so let me switch my camera. For point charge, the force is equal to, let me stop sharing for now right now so you can get a larger view. Um, point charge. So field, electric field by a point charge. Okay, field by a point charge. The electric force that's equal to K Q0 over R square, where this is the test charge. Okay. The electric field produced then is equal to K Q over R square. Okay, within that. For potential, electric potential is equal to K Q over R. Okay, so these three quantities for the electric field produced by a point charge. Okay, so for a test charge, if you have the electric force, then it's equal to KQ Q0 divided by R square. Electric field is KQ over R square, and then V is equal to KQ over R. Okay. All right. If this is three-dimensional, then the field is equal to KQ over R, where R it should be this three-dimensional position vector, the magnitude of it. So then in three dimension, you'll see it like this. Okay, so if this is a positive charge, then V is positive. Okay, if this is a negative charge, then V is negative. Okay, so if the source charge is positive, the potential surrounded is positive. If source charge is negative, potential surrounded is negative. Okay. In one dimensional, it looks like something like this. If you have multiple charges, okay, so say if you have 2-point charges in X direction, then the potential here at a positive charge, it will go to infinitely large because where this is where the charge is, right? So if you do KQ over R at this particular point, the location of the charge R is equal to 0, so then it will diverge in that location. Also, at the negative charge, then this will be infinity, negatively infinity. It will diverge at the location of the negative charge. Okay, so then this will be your overall potential. Okay, it's combination of these two. All right. So in that sense, for electric potential by several point charges, you simply just need to do the algebraic sum of the potential of each point charge, okay? Because potential is a scalar quantity, it's not a vector. Force is a vector, electric field is a vector, but electric potential is a scalar, okay? So that makes things a little bit easier. Let's take a look on the first example here. It says, as shown in the figure here, there are two charges, Q1 and Q2. All right, Q1 is positive, Q2 is negative. Positive 1.8 MC means nanocoulombs, minus 2.1 nanocoulombs for Q2, and the side length of the square is 0.1. Okay, so each side is 0.1 meters. It's asking you what's the electric potential at point A, and then what's the electric potential at point B. Okay, so remember, for electric potential, it's scalar quantity. You simply just have to add the electric potential at point A by Q1 and Q2, and then at point B by Q1 and Q2. Okay, I'll give you guys a few minutes to try to work on this. Then we can take a look at the solution together. after that. Okay. All right. So I think we can take a look here together. So charge 1 here, and then there's a charge 2 there. There are 2 points of interest A and B. All these points are on the corner of the square where the side is zero point 0.1 meters. Okay. You're looking for A, the potential at point A. Okay, so this is Q1, this is Q2. Okay, so then potential at point A should be equal to potential at A by charge 1 plus potential at A by charge 2. All right. Potential by point charge is equal to this equation there. All right, so then this is R1. In this case, this is R1 here, and then this will be R2. Okay, R2 will be the diagonal line for the score. Okay, so R1 is given, R2 you can calculate. For score, the diagonal line should be 0.10 meters, the side times the square root of 2, right? If you don't know that, you can do this by looking at this triangle here. So should be 0.1 square plus 0.1 square, and then add them up, take a square root. Okay, so that will give you that square root of 2 times the side. Okay, so that would be K Q1 over R1. Okay, for the first one, K Q1 over R1 plus K Q2 over R2. All right. For potential by point charges, you can simply just plug in the numbers here. So K is the common factor. Maybe easier for you to do K Q1 over R1 plus Q2 over R2. Okay. So then K is the 8.99 times 10 to the 9th newtons over newtons times meters over C square. Okay. Multiply by Q1, it's given as 1.8 times 10 to the negative 9 coulombs. Okay, remember to convert that nanocoulombs. I believe in some of the homework problems this time, you got the charges not in coulombs, but could be in nanocoulombs or could be in microcoulombs. So you want to pay attention to the units there. So this is Q1 divided by R1, 0.10 meters. Okay. And Q2 is negative, so you can put the negative sign here. Negative of 2.1 nanocoulombs times 10 to the negative 9 again over 0.1 meters times square root of 2. Okay. All right. So if you plug everything into the calculator, this will tell you this is about 28 volts. Okay. The SI unit for potential, it's in volts. All right. I'm going to pause a few seconds to see if you guys have questions. Okay, just unmute yourself and you can speak up. All right, if not, then we'll look at part B here. So it's asking again, what's the potential at point B? So then this would be equal to potential at point B by 1 plus potential energy by point B by 2, the charges, okay? Q1 and Q2 are the same. All right, there's a question asking about what's the conversions between different coulomps, okay? So if it's MC, that means nanocoulombs, that means 10 to the negative 9. If it's mu C, means microcoulombs, okay? That's 10 to the 9 minus 6 coulombs. If it's PC, which means picocoulombs, that means 10 to the negative 12, okay? So these are scientific prefixes. You can look them up, all right? I hope that answers your question. All right. So for potential at point B, then it's VB by 0.1 by charge 1 plus VB by charge 2. That should be equal to similarly KQ1 over R1 plus Q2 over R2. Okay, so it's going to be similar to what we did just for part A. So Q1 over R1 plus Q2 over R2. This time, Q1 and Q2 stay the same. R1 and R2, they change. Okay, so now R1 is this guy because you are looking at point B. So this is now your R1. Okay, so basically R1 and R2 kind of switch. Okay, so this is R2 then. Okay, so you switch R1 and R2 basically. So then this is equal to, you plug in the numbers, 8.99 times 10 to the 9th newtons meter square over C square. Okay, now 1.8 times 10 to the minus 9 coulombs over 0.10 meters times square root of 2. Okay, so you switch R1 R2 this time, and then minus 2.1 times 10 to the minus 9 coulombs over 0.10 meters. Okay, that will give you your potential at point B. That will be equal to minus of 74 volts. All right. So one A is positive, B is negative, okay? Because in A, you are closer to the positive charge than negative charge. So then overall, it's positive in that sense because of that. Although the charges are slightly different, okay? In part B, you are closer to the negative charge than positive charge. So your potential is negative, okay? All right. Any questions? Any other questions you guys might have on this? All right. If that's clear, we then can move on here. All right. So next section talks about equipotential lines. Okay. So remember in gravitational field, we also have the equipotential lines or contour maps. So when that happens, you are having the height at the same level. Okay, so at the same height level, you have the same potential. So similarly for electric potential, you will have equal potential lines. So for example, if you have a point charge here, if just a single point charge in a space, then um, the same distance away from the point charge because V is equal to KQ over R. So then at the same distance away from there, you will have equal potential line here. So this circular line surrounding the charge, equal distance to the charge, that will give you the same potential, okay? And then similarly here, on this green circle here, you'll have, this is another equal potential line. Yeah, and then this one and this one goes forward. Okay, the blue lines with arrow indicate the electric field lines. Okay, so that indicate the electric field. All right. All right. Um, so you can see here, pretty much for point charge, you can conclude that these two lines, the blue lines and then the green lines, they are perpendicular to each other, right? For you guys did the lab on Wednesday, you already saw that. So potential line, equal potential line, and electric field line, they are perpendicular to each other. Okay, so in theory, they should be perfectly 90-degree angles between the two lines. But in lab, of course, we have some errors there. So, but they are close. Okay. All right. So if you have like multiple charges in space, like this is the one you guys are doing this week for the lab. So for positive and negative charges, okay, you will see green lines are the equal potential lines, and then the blue lines are the electric field lines. Okay. Um, so you might have something like this, okay, depending on the distance of these two, okay. But in the middle here, you'll have no electric field. So then the green circles here are the electric equal potential lines, and then as well as this green curve here, and then this guy, okay, the oval shape, okay. All right. So for uniform electric field produced by two plates over here, so in the middle you have more or less uniform electric field. So then the line that is perpendicular to the electric field lines are the equal potential lines. Okay, so so this green line over here, they are equal potential lines. Okay, so that means at any point on that line, you have the same potential. All right. Any questions you guys might have on equal potential lines? Okay, so if not, let's move on to the next section here on capacitors and dielectrics. Okay, so after electricity was discovered, then people start to use electricity. But there's one important issue is how you can store the electricities. Okay, so one of the devices that have been invented is called capacitor. Okay, so a capacitor is basically a device that can store electric charge and energy. Okay, so it it gets the name because it has like capacity. It has the capacity to store both charge and energy. Okay, so it's called a capacitor or electric capacitor in that sense. There are different forms of electric capacitors. So the most simple one would be you put two parallel plates, metal plates facing each other. Then that would be a um, electric capacitor. Or you can have like, so this is a cross-sectional side view of this. This is actually, you can imagine that you have two metal sheets in this gray color. Okay, in between you put this orange insulator. Okay, so they are not touching each other directly, and then you actually roll it up to be in a cylinder form. Okay, so then this is also a capacitor. Okay, um, so for a capacitor, the quantity that is to describe a capacitor is called capacitance, then relates the charge to the potential difference. So you can charge the capacitor, so there will be charge being stored at the two plates. Okay, so charge being stored divided by the electric potential between the two plates gives you the capacitance. Okay, so this has a SI unit of coolant comes from charge Q, and then divided by the volts come from the volt potential V. And it's called farad. Okay, F. Okay, so for the symbol F, capital F. So in reality, so as I say, if you have two sheets that is separated by an insulator and you roll it up, so then you will get something like this. Okay, something look like a cylinder capacitor. All right. If you have just two plates insulated by a ceramic, which is an insulator, so then it will be having something like this. You can connect these two terminals to the battery to charge it. Okay, and on this guy, these are the two terminals that will charge the capacitor. You also if you have a cable wire like this, then it's itself actually is a capacitor. It has a metal in the middle here, then it has the shield, metal shield at the outer here, insulated by a separated by an insulator called dielectric here. Okay, and then the outside jacket is the housing of it, so keep the metal from exposed to you directly. So itself is actually a capacitor. Okay, all right. And you might see all these different ones. Okay, so with the capacitance will be specified on the case, with the numbers. Okay, so they are having all different type shapes for the capacitors. Okay, and you actually will use capacitors in one of the labs in about 2 weeks. Okay, all right, so let's take a look on the example on the capacitor. It says the charge on one plate of capacitor is positive 30.0 microcoulombs. Okay, so mu C means microcoulombs times 10 to the negative 6. And the charge on the other plate is also negative 30.0 microcoulombs. The potential difference between the plates is 400 volts. What's the capacitance of this capacitor? Okay. So when you use the equation C equal to Q over V, all right, so Q on one of the plate is always just the opposite sign of the Q on the other plate, okay? So if you have 30 microcoulomb on one plate, then the other will be minus 30, Okay, so the Q will be just then 30 microcoulomb. Okay, so when you do, you simply just do Q equal to 30.0 microcoulomb divided by 400 volts. Okay, so that will give you what would be the capacitance. So I think we can take a look on this one together rather than um, doing them by yourself individually. Okay, so it should be straightforward that in this case, C is equal to, so C is just equal to Q over V, all right? Q here is 30.0 times 10 to the minus 6 coulombs, V is 400 volts, okay? So this will give you 7.5 times 10 to the minus 8 farad, okay, for the capacitance of this capacitor, all right? Let me know if you have any questions on this one. All right, so just one note here. If Q is a number like positive 30 on one plate, then the other one will be negative of that, okay? All right. So if you place two metal plates parallel to each other, then this is a parallel plate capacitor. This is the simplest type of capacitor you could have, okay? So let's see what's the capacitance of a capacitor like this. So it's actually, according to the experimental result, you can actually measure this. So C for a parallel plate capacitor is equal to epsilon naught. This is a constant number, which is called the permittivity of vacuum. Okay, if there's nothing in between or free space, vacuum is free space, that's equal to 8.85 times 10 to the negative 12 in farad per meter. Okay, so for that number, permittivity of vacuum or free space, and capacitance will be proportional to the area of the plates. Okay, so you can imagine if you have larger plates, you can store more charge, right? And it's actually inversely proportional to the separation of the two plates. Okay, so in that sense, you can see like the design of capacitor in a few slides backward. Okay, so like this one, so they are pretty much just separate by a very thin insulator. Okay, so you want to make D very small to reach a larger capacitance, and then you roll the sheets up, so you will the two sheets, metal sheets will have larger area. Okay, and similarly, by on this one, you will have a small insulator in between. The two plates are very close to each other, okay, for the purpose of achieving high capacitance. All right. Okay. So for parallel plate capacitor, this is what you get. C equals to epsilon naught times A divided by D. Okay. Now, in the capacitors, we look at like this one figure shows you so many different capacitors. So there's always an insulator in between. Okay, so let's see why that's the case. Other than just keep them from touching each other. Okay, so there's another advantage here. If you place an insulator in between the plates, okay, so then you'll see the molecules of insulator will rearrange because the electric field produced by these two metal plates, right? So they redistribute, and then electric field line goes from positive to negative, okay? And then this will cancel out, this will cancel out. So for the molecules, after they are reorientated, they will cancel out some of the electric field. Okay, in this figure here, you can see the electric field lines will disappear. All right, partially when it goes through the dielectric or the insulator. So we call it also dielectric. So basically either insulator or dielectric, they are the same. All right, so you can see electric field line densities then will be reduced. Okay, so then E is reduced, then potential across the two plates is equal to E times D, directly proportional to E. So then V will be reduced. Okay, so if you place insulator between the two plates, then the V will reduce if you have the same charge Q. So then C will increase. Okay, so your capacitance will increase. All right. So that's the other advantage of putting an insulator in between the plates. Now, how much the increase of the capacitance depends on what's the dielectric constant of the insulator. Okay, so dielectric constant of the insulator is called kappa. Okay, it looks like cake, but it's called kappa. If you have a dielectric constant kappa, then electric field is reduced by that factor kappa. Okay, so new E is equal to the original E field if you have no dielectric in between the plates over kappa. All right. So then V will be also reduced by that amount. So new V will be equal to V original over kappa. Okay. Now kappa is in the denominator. Or denominator will go up. Okay. So equal to kappa times Q over V. So then the capacitance after you put insulator is equal to kappa times the original capacitance. Okay. Without the insulator. All right. So this is the dielectric constant or kappa for different materials. It gives you this. Okay, so vacuum, it has 1 as kappa equal to 1. All right, for air, it's almost like vacuum. Okay, so if it says this is in air, you can pretty much treat it as like a vacuum. And for other different materials, you can find them here. Okay, like most common material like paper, 3.7. All right, nylon is that 3.4, and then others you can look it up over here. Okay, now the last column here is about dielectric strength. Okay, so we'll talk about this, but this is like if you apply too much voltage across an insulator, then it will break down the material, make it become a conductor. So basically, you can tear off the electrons from the atoms, make them movable. Okay, but so if you multiply kappa by permittivity of space, then that gives you permittivity of the material. Okay, so epsilon equals to kappa times epsilon naught. Okay, all right. So then without dielectric, the capacitance is equal to epsilon naught times A divided by D. With dielectric, C is equal to kappa times that. Okay, so then it's equal to just permittivity of the material times A divided by D. Okay, similar expression, but this guy, the epsilon is kappa times of epsilon naught. Okay, so that's your new capacitance there. All right, so we will take a look on this example here, which says a parallel plate capacitor is made from 2 aluminum foil sheets, each 3.8 centimeter wide and 6.1 meters long. Between the sheets is a Teflon strip of the same width and length, that is 0.025 millimeter thick. What's the capacitance of this capacitor? Okay, taking the dielectric constant of Teflon as 2.1. All right, so I'll give you guys a few minutes now to work on this. We can take a look at the solution together after that. All right. I think we can take a look on here together now. So there are several dimensions given here that are not in SI unit. Okay, so first, it gives us that the two sheets each is 3.8 centimeter wide. Okay, so 3.8 is not SI unit. So then you can put that into the SI unit. Okay, um, so area of the sheet, it should be 3.8 centimeter, right? Times 6.1 meters. So you want to convert that into meters, okay? It tells you the separation of the two sheets is 0.025. This is in millimeters, okay? So you want to convert it into meters, all right? It tells you that kappa is equal to 2.1 for Teflon. So otherwise, you will just plug in the numbers in this equation over here. You can do epsilon times A, or you can do kappa times epsilon 0, which is epsilon. Okay, so times A divided by D. Okay, so 2.1 here for kappa is dimensionless. It's basically a ratio of the permittivity of material divided by permittivity of free space. Okay, so it's a ratio number there. Times 8.85 times 10 to the negative 12. Okay, that's in farad over meters times the area. Now you want to pay attention to the units here. 3.8 times 10 to the minus 2 meters multiplied by 6.1 meters. Okay, divide by the separation of 0.025, that's in millimeters, so times 10 to the minus 3 in meters. Okay, so if you have every quantity converted right, you'll get 1.7 times 10 to the minus 7 farad. Okay, that's your capacitance for this guy. Or if you want to express it in microfarad, so this is 0.17 microfarad. Micro means times 10 to the minus 6. Okay, all right. So let's be this one here. Any questions you guys might have? So if not, I think I'm going to just stop here for today and then start new section on Monday. Okay, so I'll see you guys on Monday. Bye, guys.